So we start with the short tutorials on numerical relays. We will have a series of such tutorials, short tutorials of around 15 to 20 minutes each. This first one is on transmission line protection using overcurrent and earth fault relays. So we will see as to how do we apply these numerical relays for transmission line protection using overcurrent relays and what advantages does it give for such protection. So 5 numerical relays have replaced the first generation electromechanical and second generation static relays. Why? Why at all that has happened? This is because of manifold advantages, not only with reference to quantity, that is the number of advantages, but also an added third dimension to the whole philosophy. So the first advantage is self-diagnostics, which was not available in electromechanical or static relays. That is, the relays are checking itself continuously every moment, 24 hours and 365 days. If at all there is any error in the software or hardware part of the relays, that will be announced on the display panel of the relay. So one will come to know that there is some error. Not only that, but one can have an alarm, or it's also quite possible to trip the breaker that is being controlled by the relay. Therefore, the relays are not required to be periodically tested, and therefore the reliability of protection is much better. The availability of power system is much more better than the earlier versions. The second advantage is availability of many mathematical functions and logics. It was not possible to differentiate in case of earlier relays. In electromechanical relays, if at all it could be done using LC circuits, it would need a large space and also very large time delay. In case of static relay, no doubt that is possible using operational amplifier, but once again the time delay is added, because whenever you are going to differentiate, you will need an LC circuit and charging time of capacitor is added. Whereas here in numerical relays, we are just taking the samples at every millisecond. Usual sampling interval is 1 millisecond. So we take first sample I1, say current, second sample I2. So I2 minus I1 upon delta T becomes the differentiation. Like this, you see, many mathematical functions can be done at a very large speed. Integration can be done. The harmonic analysis can be done. You can fetch out whichever harmonic you want to say. One wants to have only fundamental out of the distorted wave shape, or one wants to extract second harmonic, or somebody wants to extract fifth harmonic, or if you want to take out DC offset, if one wants to extract negative phase sequence current, zero phase sequence current, all these mathematical functions are quite possible. You can have many logic functions also, OR logic, AND logic, NAND logic, NOR logic, or these logics which are required for different interlocks in the power system applications are quite possible using numerical relays. The third very dimensional advantage is group setting. The power system is highly dynamic, right? Therefore, what happens that single setting is not at all useful. The single plug setting or single time multiplier setting is not useful. your relay has to adapt with the different conditions of the power system, the ever-changing conditions of the power system. To give few examples, we will see this, a very simple example. Say on one bus there are 4 generators connected. Now the number of generators being connected on the bus depends upon the load. So when you are making some of the generators off, say one generator is made off to cater to the newer load demand, means the load has reduced and you had to make one of the generators off, or say you had to make 2 generators off. Then the current passing through the 132 kV transmission line will change. It will be less, and if it is less, then your flux setting has to change. Not only that, but the fault current will also be different. Therefore, time multiplier setting will also be different. And in many cases, say only one generator is connected at night time, then ZS by ZL ratio will also change. And therefore, it is quite possible that you may need the very inverse relay, right? That means you may need very inverse characteristic for that overcurrent relay. So at daytime normal inverse, at night time very inverse. This was just not possible in earlier versions, which is very possible with numerical relays. Using binary inputs, you can rather change the configuration of the relay automatically. Automatically means you have to use the auxiliary switches of the circuit breaker to change the characteristic, to change the flux setting, to change the time multiplier setting, whatever newer condition, that newer requirement, and you will be able to change your settings, new group of settings. That was not possible in earlier version. Another example which can be given is something like this, that you have got 4 relays, R1, R2, R3, R4 and a parallel feeder, which is very common, right? Most of the transmission lines are parallel feeders because you can transmit double the power through the transmission line. If one line transmits 100 megawatt, 2 will transmit 200 megawatt from one place to the other. But the problem with parallel feeder is this, that if my total load is, say, as it is given in this example, total load is 1000 ampere, then if both the feeders are on, both the transmission lines are on, then 500 ampere is passing through each line, and therefore the flux setting of relay R1 and R2, I am telling R1 and R2 because R3 and R4 are going to be directional, looking away from the bus. Therefore, they are not going to operate for load current. But R1 and R2, because 500 ampere is passing, that takes me to flux setting of R1 and R2 as 50%. But I cannot go for 50%. I could not go in earlier versions of the relays because you see, if one of the line trips, if there is a fault in one of the lines, then that line will trip and total 1000 ampere will flow through the remnant LD line, and therefore the flux setting has to be 100% because 50% will trip that LD line also. So if you go for 100%, then you are reducing the sensitivity because normal current is just 500 ampere. Normal current is just 50% of 1 ampere, and therefore the sensitivity of the relay is reduced. The relay is insensitive. When I was using electromechanical or static relay, I was doing at the cost of sensitivity. Right? Now here, if I have a parallel feeder, what I'll do? If both the lines are on, my setting, flux setting for R1 and R2 is 50%. And if one line trips, it automatically changes to 100% using the breaker switches of that line which has tripped. The auxiliary switches of breaker CB1 or CB2 I will use. And I'll change the flux setting of R1 and R2. Similarly, because both the lines are on, the fault current will be more. If one line is off, then fault current is going to reduce because impedance is going to increase. So time multiplier setting also will change according to the new condition. That is one line contingency. And I am talking about only two buses and two lines. In an interconnected system, there are 50 transmission lines and many buses. So obviously the number of permutations and combinations are many more. And in these conditions, your relay has to match with the newer requirement. Nowadays, the modern numerical relay manufacturers, very renowned relay manufacturers, give us as many as 6 groups of setting. Not only that, but they give us about 16 binary inputs and 16 binary outputs. So with these things, the relay takes us to a very good kind of protection and a very good sensitivity, very good reliability. And the best thing is very much more availability of the power system for more time. So that is the advantage. Storage of fault current data and event recording, right? That is the another advantage. Fault currents are available, not only one, but as many as 32 last fault current data. Not only data, but what was the harmonics in the fault current? What was the DC offset? Not only that, but you can have a wave shape plotted on the graph, time graph. The readily plotted wave shape will be available at the time of fault. Right. And any event that occurs with reference to protection, with reference to normal operation also, either any breaker is on, either any breaker is off, something happened in the system, that those events are also recorded. Metering, control and protection. So it does very good, much better protection than the earlier relays. More so, it gives us the advantage of metering. The relay can measure current, voltage, active power, reactive power, power factor, negative sequence current, negative sequence voltage, zero sequence current, zero sequence voltage. Many quantities are available on the relay. So you save the cost of meters, either digital or analog meters. Cost is saved, the space on the panel is saved. A very small panel, very miniaturized panel is enough. Over and above that, it does many control functions. Say the next function, circuit breaker failure protection, is one of the control functions, right? Breaker on and off you can do from the relay panel. You can do from relay itself. So many control function. Say the trip circuit supervision is one of the functions. So many such control functions are possible. One very important advantage is circuit breaker failure protection. This was not available in earlier relay. The relay gives signal to the breaker if breaker somehow fails, and breaker can fail because of many reasons. Breaker can fail because there is trip coil has become open circuited. If there is an air blast circuit breaker, the air pressure is not enough. If it is a SF6 circuit breaker, the pressure of SF6 is not proper. Some leakage is there. The operating mechanism is giving trouble. Because of many fault reasons, circuit breaker can fail. But the earlier relay was not letting you know whether the circuit breaker is working or not working. And if circuit breaker doesn't become off, the fault is continued. Fault is because fault current interruption is done by the breaker. So fault is yet persisting. Relay has operated correctly. Now these relays are telling you whether the breaker which is being given the signal by the relay is operated or not. That is very simple. Say there is a fault at F. I have got an incomer and 4 outgoing feeders. On incomer I have got a relay R1. On outgoing feeder I have got a relay R2. Now if there is a fault at F, that fault is going to be cleared after say 0.1 second, that is 100 millisecond. So maximum within 20 milliseconds for the most accurate relay algorithm, right? Full cycle Fourier algorithm, within 20 millisecond relay will come to know, relay R2 will come to know that there is a fault. Relay is going to operate after 100 millisecond, but after 20 millisecond, it will come to know that the fault is there. Now it will give signal to breaker CB2. CB2 did not operate. When CB2 does not operate, fault current is yet passing through relay. Fault current is not stopping. Therefore, relay comes to know, because it's a well-programmed relay, it comes to know that the circuit breaker CB2 has not operated. So it will generate another signal which you can use to trip the upstream breaker CB1, or you can use to sound an alarm, whatever you want. But relay will tell you, relay R2 will tell you that CB2 has not tripped. Not only that, but the another facility is reverse interlocking. That is, relay R2 senses the fault within 20 milliseconds. Once it senses the fault, it generates a start signal. And that start signal can be used to block the operation of relay R1. So now the time discriminative margin between R1 and R2, some 40 millisecond is enough. In earlier days, we had to go for 0.25 second or 0.2 second, some 200 millisecond or 250 millisecond. Instead, 40 millisecond is more than enough. Now R1 will operate much faster than in earlier case, because that facility of reverse interlocking. Reverse interlocking means blocking relay R1 when R2 senses the fault. If there is a fault on the bus, then R2 will not at all sense. In that case, R1 will operate much faster. That is starting function and blocking function, which is so often known as reverse interlocking. Auto multiplying the setting during transient conditions. So you can multiply the setting. This is very important, because when you are energizing a transformer, the magnetizing inner system 10 times the rated current in the worst case. When you are starting an induction motor, the starting current is 6 times the rated current. Now for this inrush current, for this switching in current, if the relay operates, that is wrong. Therefore, you had to keep at least the setting of high set unit to a very high value. In case of motor, the setting of high set unit has to be more than 6-7 times, and in case of transformer, it has to be more than 10 times the rated current. The rated current of the transformer, or so to say, the rated current of the relay, more or less. So you see, if a transformer of 100 ampere is being energized, some 1000 ampere will pass. So your high set setting has to be more than 1000%. But if there is an internal fault taking some 500% or 600%, then the relay will operate after time delay, because instantaneous setting cannot operate. That was happening in the earlier days. Now in these newer relays, whenever you switch on the unit, motor or transformer, the setting of high set unit automatically multiplies itself 3 times, 4 times, that is settable. 2 times, 3 times, 4 times, whatever you want to do. So it will go to a higher value. Therefore, you can set the instantaneous unit at a lower value, right? And when the normal condition is resumed, when the normal current of the transformer or normal current of the motor is resumed, that multiplication is withdrawn, the setting resumes to its normal value, right? This auto multiplication facility is available in the modern relays. And one very important facility is switch on to fault, SOTF. It means whenever you are switching on to fault, when fault is already existing, say earthing switch is on and you are making the breaker on, therefore fault is already existing. So why to go for a delay? Particularly breaker at one end and earthing switch is at the other end of the transmission line. Which other end switch will go to second zone of distance relay, or it will go to the time delayed zone of the overcurrent relay. So you will take time. The relay will take time, but this facility finds out that when the circuit breaker is switched on, immediately the current has gone from 0 to very high value. Therefore, it will be sensed and the the relay will initiate instantaneous tripping. So these very important advantages are there in the modern relays. So when you apply these relays to the overcurrent and earth fault relays, these important dynamic advantages are available. I request all of you to stay tuned with AdaptMe to see the latest news, the more and more modules which will be put up. We'll be going into the application of numerical relays in distance protection, application of numerical relays for induction motor protection, application of numerical relays for generator protection, transformer protection. One by one, we will take each equipment. Such short videos will be available on AdaptMe channel. So please stay tuned to the channel of AdaptMe. Thank you. Good day.